I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this very interesting and enjoyable synthesis of styrene, C8H8, and the representation is before you. Why is this such an interesting molecule? Because every carbon is attached to a double bond in some form. There's a carbon here, there's a carbon here, there's a carbon here, and every single carbon, there's one over here, obviously here and here. Every carbon has a double bond. Simple as that. Every carbon is sp2 hybridized. Excellent compound to analyze. C8H8. Benzene, you know, to be C6H6. So what have we done? We've added two more carbons and we've added two more hydrogens to arrive at styrene. And how do we do it? Let's examine. Start over here with acetic acid, RC double bond OH. Reacted with thionyl chloride, SOCl2. And then what are we going to get over here? We're going to convert this into a acetyl chloride, RC double bond OCl. You'll have some byproducts, HCl plus sulfur dioxide. You're starting here with acetic acid, reacting with thionyl chloride to arrive at this. We need this acetyl chloride, HClSO2. This is what we need. Now we have benzene. This is our basic representation of benzene. You can represent it like that, because when you look at the benzene, it has two resonance structures. One looks like this and then the other looks like this, where you're just alternating the double bonds here and here. The interplay of this can be in this form right over here, where everything is represented like that in terms of a resonance structure. Then you represent it in an abbreviation or a shortcut as that, and there's nothing wrong with that representation. So we have benzene. Now what we do is reacted with our acetyl chloride in a Friedel-Crafts acylation reaction, RC double bond OCl, catalyst AlCl3 in an acidic environment, H plus H2O. This right here is Friedel-Crafts acylation. Acylation versus alkylation. Here you're adding an acyl chloride versus an alkyl chloride, hence acylation, ACYLATION. Friedel-Crafts acylation reaction. It's going to bring this item and it's going to bond it to our benzene, and this is what we have, acetyl benzene. If you want to call it that, nothing wrong with calling that. This item has been added here. This chlorine has been gone away. It reacted with one of the hydrogens, because you know there's always a hydrogen here. It reacted with the hydrogen. You would have had HCl, but I'm not showing that. We can eliminate that. Now we have this. What we have to do is reduce this carbonyl group into an alcohol. We can do sodium borohydride, NaBH4. Or you can also do lithium aluminum hydride, which you will say LaH. Lithium aluminum hydride or sodium borohydride, these are your reducing agents. They convert the carbonyl into an alcohol. And you will do this in the presence of alcohol, ETOH. And what you will end up with is this, CHOH and CH3. My carbonyl functionality has been converted into CHOH. Both of these hydrogens came from right here, the reducing agent. Now we have our alcohol. All we have to do is eliminate, meaning we have to dehydrate this alcohol and generate our end result. How will we dehydrate it? In the presence of an acid and heat. You will protonate this OH to become a water, it'll drive off, and then we'll get our end result here, styrene. And it'll be CH double bond CH2, and here is our end result. We have eliminated the OH group. It has been driven off by protonation in an acid heat environment in an elimination reaction, and we've developed our end product, styrene. So what is it? It's not hard. Develop your acetyl chloride from vinegar, acetic acid, reacted with benzene in a Friedel-Crafts acylation reaction, reduce your carbonyl group into an alcohol, and then drive away your alcohol in an elimination reaction, and you're getting your alkene functionality. Now you have your styrene, and we are done.